I bought the tank about 3 years ago now, and it's been at the last 3 exhibitions. Strangely enough, I just wanted it because of what it was, but I also knew that it would be a sort of a test bed. And when I came in here tonight, Kevin said it'd be nice when it's finished, and we expect that from Kevin, obviously, but there's some truth in that as well. It never really will be finished. It's a sort of test bed for things. So a lot of what you see here today will be things I've just decided to get stuck into and experiment with to see how I can make it work. And so, some of it is also uncovering mysteries and things I've not done before, so I've just sort of muddled through with those as well. Now, I hesitate to say this isn't the sort of talk we normally have, because we have a wide variety of talks. But I think there might be some stuff in here that some of you are not so familiar with. So rather than turn it into a tutorial about computers and things like that, which would be misrepresenting the title, I'm still going to try and give some basics in there that might help you get your head around what I'm actually talking about. But I would encourage you to try and follow what I'm going through as best you can, and then you'll see more clearly how I've gone about trying to fix some of the challenges I see in a model like that. If that all makes sense, I think that's enough of that. So it really boiled down to making it more usable and realistic. And in fact, the culmination of that was at the last exhibition in September, where my objective was to get it to the point where youngsters could actually drive it safely. Up until then, the previous 2 years, it had just been me driving it around and pretending to shoot small children as they hid behind their parents' legs or crush them under my tracks. No. So, and there it is. Actually, on the very first time it turned out, it's a bit more battered and dirty now, but that was it, sitting there waiting for the exhibition to start, or the show to start, in probably, I think it was 2022. That was the first one. So this particular year, for those of you who didn't come along to the exhibition, kids as young as 6 would be able to operate the radio control and drive it round a circuit safely. But they wouldn't have been able to do that. Well, often they didn't do it very well, but they wouldn't have been even worse if I hadn't have made the mods to the tank. Okay, so the experience led me to realise that starting the tank slowly and in a realistic way was difficult. And sometimes your preconceived notions about how it actually starts, the motion of starting a 55-ton tank that is basically a bit underpowered, with a gearbox that is a pre-selected 8-speed semi-automatic, where you need to maintain 1900 revs in order to keep the oil pressure up for the gear change to actually work, is all a bit tricky, and it has its own unique sort of moving style. And of course, being heavy, it's got another sort of appearance in the way it moves, okay? But starting was tricky, and it kind of lurched off the line, because you move the stick forwards, and then all of a sudden it would just lurch forwards. And that was quite, firstly, it didn't look very good. And secondly, when I was trying to put it inside and outside the car, it was really difficult coming down the ramps. I had an automatic car once, and in the early days, and I read a review of the car, and a motoring journalist described it as, you need to book an appointment with first gear. So basically, you'd put your foot down, and then it just lurched forwards. And of course, this caught my wife out every time. So it didn't go. When she put her foot down, nothing happened. So she put it down more and more and more. And then all of a sudden, she'd just catapult onto the roundabout. Bit like that. So manoeuvring into the car was very risky, and more than once I found myself with the tank doing a sudden twitch, and the tank moves a little bit, but the track drives the ramp backwards or forwards, and I'm starting to think I'm going to crash into the car and lose the whole thing. So that was really hard. I've talked about the aggression of the acceleration. Okay. Also, when going flat out, that's too fast. Now that's something easy to fix. It should be anyway. When I let go of the joystick, it just screeched to a halt. Okay. Now, so I guess maybe that's what a real tiger did one day. If there was an emergency stop, and perhaps that's not unreasonable behaviour. But what it meant was that you had to use the stick to slow it down, and perhaps I wasn't expecting enough of myself in terms of controlling it with the joystick. But there were no gear changes. The real tank, as I said, had 8 speeds, or 8 gears, and they had to be used. That has no gears, or 1 gear basically, and that's it. So that was an opportunity, that was an area that it needed to change. The sounds. Right, so I'll come to that a bit more detail about this later, but they were very difficult or clunky to actually initiate each sound. And to be honest with you, you need a little printout of the information next to you to know how many times to flick switches and stuff like that, or you've got a memory of it all. So that needed to change too. If kids were going to use it, I needed to take precedent over whether the tank was to continue moving or not. I needed to be able to switch it off from a distance. And I spent a long time ploughing through the radio control manual, trying to understand what its capabilities were and what its limitations were. And eventually I think I got there and figured out the limitations of it. And some of the things I was trying to do at the top there were going to be hard to do with the radio control capabilities. I'll still be prepared to be corrected on that if someone can show me how to do it with this particular radio control. And of course, when it's driving around, the battery's going down at a rate of knots. And I had no way of knowing what the battery level was, the voltage on the tank. So it was it was something I wanted to do, was to get a sort of a display on my radio control showing me the battery voltage. Okay, so you can see some sort of vague chapter headings at the top, and I set them out and then decided to change the order recently. So don't take too much notice of those. We're going to look at security. It's a strange title. It covers a number of sins, but it covers some of the basics of what I did. So the emergency switch off, right? So where I've got the switches, the on-off switch of the tank is under one of the rear vents on the deck of the tank. And that's all very fine and dandy, but you have to actually lift it up and flick the switch to turn it off. The other thing, of course, is if the turret is in the wrong position, it snags the vent that comes up. So that was a problem. The other thing was, talking of using amps, if the smoke unit was on, the battery would drain about 3 times as fast. And so it would be useful, so I could just stop the tank and and walk away from it, but it's still live and the smoke unit may still be on, so that needs to be physically switched off as well in the same area as the on-off switch. And I haven't got remote control for the smoke unit yet, because basically that's just a heating element, so the battery just drains through this heating element. So I need to be able to stop, that's true, and when kids are doing it. And the other thing is I didn't want to be any risk, even through my oversight, of someone just picking up the radio control and started driving the tank when I'm not around. So these things needed to be fixed, and basically I fixed it with a remote control switch. Now, some of you will have seen this before. This is the way I've wired up the tank. So there's a sort of a multi-pole, 4-pole switch, which basically switches it from 24 volts, the batteries in series going to the tank. Oh, hold on. Like that. So you've got the batteries connected in series. And then when I want to charge it, I just use a 12-volt charger and I flick the switch, and now I've got them in parallel. And I took care when I was buying the switch to make sure that it was it broke the contacts on one side before it made the contacts the other side. Most places you buy these sort of switches from won't even tell you that. So you have to go to somewhere like RS, and you'll get more information than you could ever think you needed from them. But that's great, because I was able to find the right switch for that. So given that, I wanted to so the original on-off switch is a solenoid type switch, so it's a solenoid that's powered by the tank, and that's okay, but that's just a standard way of using a small switch to switch a large current, or large current wires. So what I did was I put a radio controlled switch after that to power the tank. So it sort of overrode it, if you like. And well, they're in series, so they both have to be on for it to work anyway. But it means that I can switch the tank off remotely. And this is pretty much it. This is revert to China, basically. What we've got here, oh, hold on. What we've got here is a little fella that was bought from eBay, and it advertises, you know, for roller lines and all sorts of things. So it had the power, the current capacity, it had the voltage capacity. The range was fine, even though I was going to stick this in the tank. The range is absolutely fine. The aluminium shell of the tank doesn't seem to act like a Faraday cage at all. I've not had any trouble in that sense. So you'll see when you look at the tank later, you'll see the fob sitting on the rear deck. I'd normally, if I was operating it with children running it, I'd just have it on my belt or something, and I would be able to switch it off, even if, you know, because you know what kids are like, right? There was at least one child who just refused to take any instruction whatsoever. At one point, I said, I want you to stop the tank. No, I'm not stopping it. If you don't stop it, I'll stop it for you. No, you won't. So, yeah, so this came in quite useful a couple of times. Especially when it was about to fall off one of the little bridge I'd made. And of course, if it falls off the bridge, Muggins here has to put his back into lifting the flipping thing back on it. So anyway, back in the engine room, that's the sort of power connector thing, if you like. This is where the battery power goes in, and outside the other side, you'll see it again when I take the lid off, there's a load of connections here going to the various consumers of power. So just power in, power out, and out it goes to the main end. And this one's come from, that's the little solenoidy thing that's connected to the switch somewhere else. So that was quite straightforward and very satisfying. It worked. I've even got a spare fob. So that was really cheap. That was about £12 or something like that, or £15. It's just nothing really. Okay, the voltage. So we all want to know what the volts are, and you can never have too much data, can you? So, you know, this is about getting the volts coming up, volts on the of the tank coming up on my radio control screen. So this is my receiver, It's an FR Sky, however you want to pronounce it, 8-channel receiver. And so you can see the 8 channels running down there. And then it's got something called RSSI, which others will know more about than I, but that's receiver signal strength indicator. And I think, if I'm not too mistaken, I think that's actually an output. So it's a little 3-pin thing. It'll take a normal sort of 3-pin servo lead. Yeah, it's an output. And output, it says. So I'm not... Anyway, that basically allows the object that's being radio controlled to know what the voltage is, I think, or the signal strength is, rather. Now, this is really courtesy of the fact that pretty much every radio control device you buy assumes you're going to fly an aeroplane. All the controls on it tend to be named after the sort of controls you would use flying an aeroplane, like aileron and blah-de-blah. Which is a little bit frustrating, but it's not the end of the world. They're just names at the end of the day. But the one that was more interesting, well, okay, so S-Bus, I'll just tell you what that's about. Channel 1 to channel 16. So it's got a very snazzy way of just doing 16 channels instead of 8. If I just buy another one of these, I can connect it up using the S-Bus port to directly to another one. So that they connect these two together and they'll work as 16 channels, which is quite nice. That might be something I need to do because I've pretty much run out of channels already. The bit that helped me do the telemetry was the smart port. This is a FR Sky proprietary technology, and again it uses the standard leads, three wire leads for radio control, and this allows you to essentially daisy chain things together. So, and this is where the telemetry device comes in, because what I did was I bought a FR Sky telemetry device for voltage, but you can't just get a voltage one. It's got 2 other sensors on it as well. It's got temperature and current. Well, that's great, isn't it? I mean, I'm not going to complain about having more data. The temperature one's not really very helpful for me, because I don't think temperature is really something I need to worry about inside the tank. Unless I was operating in really cold regions, I might want to know that the lithium batteries are going to give up on me at around about 1 or 2 degrees, as they do for my bicycle lighting. Right, so it's all fairly sort of minimalist, and I suspect that's because they don't want any additional more weight than they need, because they're assuming it's going to go into an aeroplane. But that doesn't tell us a lot. Right, so this is how it was connected. So basically you just connect it to that special port using a cable, and then you can see the connectors there for daisy chaining it if you wanted to just daisy chain it onto another device you bought. The power cable goes through that ring there. I don't know whether that's a hall sensor or just a coil. It measures the changes in current. If it's a steady DC current, it's certainly not going to give you any changing magnetic fields, but someone might know better than me as to what actually is in there. But I just wired up the voltage going to the main distribution box to there, soldered it to the pads, and then that's just hanging around inside the tank, the temperature sensor. And I put it all in this box because it's already untidy enough in the tank, with enough wires all over the place and bits rattling around and stuck on by Velcro, that this at least helps a little bit. So this is what it looks like. Now, the great thing about it is I plugged in this telemetry, the sensors, powered it all up, went to a special place in the control, in the setup for the device, the radio, as it says in the manual, and just clicked on detect devices. words to the effect. And instantaneously it had found the 3 sensors and presented them to me. When I go onto the telemetry screen in the setup, which I'll come to later, it gave me these 3. Current, voltage, temperature. And gives me the opportunity to set, so I chose gauges, okay, like fuel gauge type things. And you give the minimum and the maximum. That's not really any kind of limit on the current or voltage. That's simply the extent of the ends of the ranges there in the gauge. So there we go. That's just sitting there in the garage at 10 degrees. 1.1 amp is what it draws, doing absolutely nothing. And the voltages are pretty good at that point. And it also gives you this for free as well, which is the RSSI in actual fact, but it's shown on my radio control. So as I was standing right next to it, it was obviously quite a good.
Signal strength, is that?
Yes, in a percentage. Okay, so that was all delightfully straightforward as well, and very enjoyable to do, because you felt like I was achieving something. I changed the batteries. I had lead acid sort of recreation deep discharge batteries. They were great, but after 2 long weekends and a few other bits of usage, they were already showing signs of weakness and I needed something a bit stronger really. So I bought a couple of LiFePO4s, lithium batteries, and they've been very lively and done a good job. The problem was, of course, guess what? They're just a different size, aren't they, to the lead acid ones? What is that all about? But anyway, they were taller, and it was already pretty tight. So here's the underside of the turret. That is a sort of a rotary connector there, so it allows the turret to just go, and the electrical connection, the wire's not getting tangled up. But of course, it sits quite low and in the centre of the turret. But this is pretty much the only obvious place to put the batteries in the tank. So I found it snagged. So I had to put these sort of standoffs in here and try and raise it up a bit. The next solution, if that wasn't going to work, it does work actually, but if that wasn't going to work, I was actually going to split the batteries by about 5 centimetres to give it space for the cable to not get snagged. But they're working tremendously well, and if you're okay with they're coming down in price quite a lot already, but if you're okay with the initial capital cost, they're going to be cheaper in the long run, no doubt about it. Okay, so that was straightforward as well. Sounds. This is where it gets a bit more complicated. So here are the sounds. I've got 9 sounds, 9. I typically don't use most of them. I only use engine start and stop, which is number 1. I don't even bother with engine revving. It automatically revs when I go forward with because it's linked to the speed controllers for the motors. So as the pulse width changes on those, there's a wire that connects to the sound unit and the revving goes up. But I use the main gun sometimes and the machine gun sometimes. I don't bother with 5 through 9. Although if they were available more easily, then I might do. So how does this work? Well, what you have to, basically the thing to remember is the connection between the radio and the sound module in the tank is only single channel. And you've got to connect it to a 3-position switch on the radio. So what happens is, you've got this 3-position switch. You have to waggle it up a given number of times, up and down up and then back to the middle a given number of times. And then the final time, you switch it down and then back up to the middle to initiate the sound. So to get sound number 9, I have to go 1, 2, 3, 4, 5, 6, and so on, and then sound. So it's not very sort of you can't use it impulsively really. You have to plan. And there's a switch there, right? So here's the waggling. Up, and then finally, yeah, something like that to get sound number 2. So that had to go, obviously. So what did I do? I couldn't figure out, well, okay, there is a way of doing this over one channel. And I'll revisit that when I've gone through the radio control stuff. But for those of you who aren't experts in radio control, here's a bit of radio control stuff. So radio control signals on a per channel basis fly across from the radio to the receiver and then get punted out to the servos and whatever else it is you've got. And each channel, if it gives you a pulses of 1 millisecond, that is basically one extreme of the number of pulses. So then it can pulse anywhere between 1 millisecond and 2 milliseconds. On the radio, the terminology is that that one is minus 100. 1.5, i.e. halfway between 1 and 2, is actually 0 on the radio, and this is plus 100. In actual fact, what you're getting is 1,000 microseconds, 2,000 microseconds, or 1,500 microseconds there. And so with a 3-position switch, by default, if the position is in the centre, it's spitting out 1.5 millisecond pulses down that channel. So what the Armatech, that's the manufacturer's technology, is looking for at the other end in the tank is, when I do the pulses, is something, well, hold on a minute, I'll just cover this bit. The way it works is roughly every 20 milliseconds, there's the 8 channels are transmitted. And so this gets squirted out of the radio, the receiver picks these up and says, well, okay, this is channel 3, it's this long, so I'm going to do this. I send that out to the servo or whatever it is. So if you think about it, these can be a maximum of 2. You've got to have a gap of some sort there. So you've pretty much eaten up 20 milliseconds. So that's a 50th of a second. So this is a sort of 50 hertz type thing. It's getting 50 batches of these every second. And the thought then occurs, well, how do you get 16 channels? So the reality, in my opinion, is this is just straightforward old tech. And these days, you don't really care what goes on between the radio and the receiver as a consumer. All you're interested in is what goes on at the radio and coming out of the receiver, which means that the manufacturer can do what the heck they like between the radio and the receiver. And so they can squeeze 16 channels just by squirting more of this down between to the receiver. And then FR Sky, with their extra 16 channel capability, just interpret this and it comes out as 16 channels the other end. So engine start stop, that was number 1 on the list. So what we do is we have an up flick, a back to the middle flick, and a down flick. Now, of course, it's going to take me about a second to do that, isn't it? So you're going to get about 25 of these signals going down for my up flick, about 25 or so for the back to the middle, and another 25 for the down before I return the switch back up to the middle again. And similarly for these as well, the main gun and the machine gun. Okay, so that, armed with that information, I basically decided to just choose 3 of those: engine start stop, machine gun and main gun. And what I did was allocate each of them their own channel. And then put an Arduino computer to read those 3 channels coming out of the receiver. And then what I would do is use the Arduino to mimic the up and down switches as a single channel into the sound module. Now, this, for the electricians amongst you, wake up, Mike. This is basically the way it's all wired up. You've got the receiver there with the 8 channels, a 24 volt to 5 volt converter just to give power to the Arduino. And then I've got the track motor controllers, the ESCs there, and the sound controller, basically under the control of the Arduino now. I'll talk about the track motors in a minute, but we're talking about sound at the moment. So out of pin 11 on the Arduino, that gets taken across to sound. Now, obviously, when you're connecting all this stuff up, one of the things you've really got to make sure of is everything has got the same idea of ground, or neutral, as it were. Not so much ground, but just a common earth, or common neutral. So there we go, that's the black floating all over the place. And the way that Armatech have implemented it is that either of the track controllers, the ESCs for the tracks, provide power back to the receiver. There's no separate power supply for the receiver. It just sucks it in through one of the standard issue servo cables, three wire servo cables, and it gets it from the track motors who've got ample power coming from the main distribution. So there are the channels coming in from the receiver for those 3. So it'll be 5, 6, 7, and 8. These resistors are important. They ground the signals going into the Arduino. Anyone know why that is? Why that's important? Stop noise. The noise is not a problem when it's all switched on. The noise is a problem when it's not all switched on. So, for example, if the Arduino was switched on and there was no power to the receiver, these wires, these inputs would just float. And as they floated up and down, they would be interpreted as noughts and ones by the Arduino, and the Arduino would just blind faith, take those and convert them into signals for the track controller and the sound controller. And that happened to me once. This didn't have power, that didn't have power, this did, these did, and the tracks just started working like they were under their own control. There was it's like sort of jinxed in some way or something. It was really weird, but also quite dangerous. Fortunately, I had the tank jacked up, so the tracks were actually off the ground when it was happening. Otherwise, it would have just started moving around. So what these do is guard against the situation that this power's powered off and that's powered on by holding these inputs to one logic level. So as far as the Arduino is concerned, absolutely nothing's happening on those.
If I remember correctly, it was a long time since I've come much back from Arduino, but I have a feeling that there are internal pull-up resistors that you could enable.
Yes, there are.
There are?
Yeah.
Yeah, but you decided...
I just wanted to be on the safe side. Yeah, you can.
What value resistors did you use?
Well, Kevin, yellow, mauve, orange, gold.
Yeah, but there's so many of them.
Come on, who knows their resistor colour codes?
47K. 1K?
47.
Yeah, yellow's 4, purple's 7, orange I think is 4, is it? 3. So you've got 47K, that's right. 47 times 10 to the 3 or something. Well, 40. It's actually more like 47000, isn't it? Orange is the number of zeros, and then the gold just tells you the tolerance of the resistor. To be honest with you, it doesn't matter what they are, as long as they're a few K. You don't want to be just draining current through there unnecessarily. So there we go. I'll probably show this diagram again because actually it looks complicated, but it's actually fairly straightforward. So, and there's a little 5 volt thing. That's another few quid from eBay again, which just takes a voltage and spits out 5 volts for the Arduino, so that it's got its own power. Right, so just a bit on Arduino now, so you know what I'm talking about when I mention Arduino, because it might be a strange word for some of you. It's a little computer, nothing more, nothing less. And in fact, that is the guts of it, okay? Shame it's upside down, but it's made by a company called Atmel. People would generally refer to this chip as something called an AT Mega, would be one way to refer to it, so quite useful. And on the Arduino board, and it's about the dimensions of a packet of fags, 20 fags, not 10. And there's your USB port. That's your USB chip to take care of the USB signal going through there. And you get some little LEDs here to tell you when you're transmitting and receiving, so that's handy. This is the crystal and the oscillator circuit here. Actually, no, that's the oscillator circuit, but that is the crystal for it. And that's what provides the 16 megahertz signal into your chip. This is a power jack, 5 volts. And then what you've got down the side here, and that's a reset button there. What you've got down the side here, and this side, is a couple of headers, and they're basically sockets for all the inputs and outputs that the Arduino is capable of giving you, which is pretty good actually, for something that isn't particularly advanced. So you've got the ones with the squiggle after them are all capable of being configured to do digital pulse width modulation. So these are typically the pins I would use to connect out to the ESCs on the tank and the sound board, because they expect radio control servo type pulse width modulation. So the fact that the Arduino, courtesy of this AT Mega chip, is able to understand how to generate PWM using some simple software commands inside it is brilliant. You've also, if you wanted to actually measure analog signals, you can put them in here and it will turn it into a digital number. So it's an analog to digital converter built into the chip. You've got various other connectors here for voltage mainly. Several general purpose pins for inputs and outputs. So it's quite remarkable. But think about the speed. So in your, if anyone's got an iPhone 14, 3.2 gigahertz is the clock speed in that. I mean, when I did my summer job when I was about 18 years old at Philips Research Labs, I was assigned to the lab that was doing work on microwaves and using them for battlefield radar and stuff like that. This is microwave territory. That's astonishing. The current x86, 6.2 gigahertz. The limitations generally are, even though it doesn't seem to be much of a limitation because they keep going up, is starting to be not the actual thickness of the tracks in the chips now, it's down to the power dissipation and the difficulty in doing that. But anyway, the very first PC that emerged in the 80s, 4.7 meg. So we're doing a bit better than that, but not much. But do you know what? This is easily fast enough for what I'm doing. And I've even had to put delays in my code to just stall and wait a bit. So Arduino, very, very useful.
Mike, did you know, I see it's an R3, that the R3 and the R3 Wi-Fi draw less, you can't draw so much current as you could with the earlier versions.
Is that so?
You've got to be so careful with what the current drawing is.
Okay.
Because you can blow them up. Just let them know.
No, fair enough, thank you. It survived so far. Now, the other good thing about them is these headers that run down each side, this is in the tank, they're quite handy because there's a whole load of what are called shields. It's just a name the company's given to basically boards that you can just plug in. So there's a whole load of pins here, and it allows me to plug this sort of board in, which has given me the opportunity to do a bit of circuitry on it. So I've soldered in a load of circuitry, including some pins to take the servo signals, take them into the Arduino and send them out to the things that consume the signals. The resistors are there on there too. So it's a bit tatty, isn't it? But so basically I've used that to make it as a simple wiring loom. Okay, what else? So why did I choose Arduino? It's really, really cheap and simple is the real answer. It's not a challenge in itself. There's plenty of ways of getting a challenge in this world of microprocessors, microcomputers if I really wanted to, but I didn't. And you know, if you've got a PC, you'll have version control issues sometimes, don't you? You'll have a driver issue. You need a driver's incompatible with something else. Not so much these days. The world's a bit better now, but because Arduino is conceived and produced by one company, they kind of control it all, even though you could say the same for Microsoft, I suppose. But you don't really have version control issues with this, particularly. Because you've got a single governing organisation. Its connectivity is fantastic, and it's such a great ecosystem. If I can buy shields for it to do all sorts of things, and there's so much code that can be reused on the internet, displays, sensors, you name it, it's all there, really easy. Only 25 quid, actually you can get them cheaper if you're prepared to buy a knockoff one. And programming language is C or Python. If you've got kids, they might know Python. If you've got someone old, they might have been brought up on C, like me. So that was attractive for me as well, because I knew that I'd be able to sort of get up to speed okay.
Spectrum Basic.
Well, do you know, I wouldn't say there isn't a basic for this, because I'm sure someone will have implemented it to... so if you want to have a go, Frank, dig out the basic compiler for this.
It's one that I did many, many years ago.
Yeah. I think that was probably my first language as well. In school, the school had a Commodore PET, and that used BASIC, if I remember rightly, with your line numbers 10, 20, 30, and you had to space them out to give yourself the opportunity to go back and fix the code and stuff like that, didn't you? But it was a great start, wasn't it? Great start. So, no more computing after this, but again, this is going to become helpful. One thing these computers don't do, they don't stop. They just keep going. If they're apparently not going, they're probably just looping, doing nothing in particular. But they're still chewing through their instructions at somewhere close to 16 million a second, just for an Arduino. If it's your iPhone, it'll probably be chewing through them at 1,000 million instructions a second. It's just mind-boggling. And what actually happens is you have some program members. So you'll have a program, we all know about applications and stuff, and it's got code in, hasn't it? Well, that's where all the instructions are for the computer. And it's typically something that's read-only, because you don't need to change it. In the old days, it used to be on disks that you wouldn't change. So it goes into the control unit. The clock, we've seen the clock on the Arduino, that just gives it its relentless, restless sort of constant operation. So every time a clock beat goes in, it operates based on the information it's got in the instruction it's looking at, and then it may involve getting another instruction, or it may involve doing something useful for you in the arithmetic logic unit. We have inputs. We saw plenty of inputs on the Arduino and plenty of outputs. They're the same as these. And then we have something called data memory. Now this is basically your short-term memory. It's like if you're doing some mental arithmetic and you keep a few numbers in your head. That's what this is. It's non-persistent. Well, actually, it tends to be more persistent these days, but it's stuff that can change. You can write to it and read from it. So this does simple literally arithmetic, sometimes binary arithmetic, sometimes decimal, does comparisons, conditional jumps around the code, all sorts of things. But basically that's it. That is simply a computer. But just remember, it just keeps going. And on the Arduino, your basic program structure when you're writing your code is you do some setup stuff and then you dive into the main loop. And once you're in that loop, you just don't come out of it. You just keep going forever until you hit the reset button or switch it off. So that's the way it works. Here's an example of something you could do. This is really easy to do. It's probably one of the first projects you'd do if you'd got an Arduino. So what we've got here, a potentiometer, and using this breadboard here, we've connected it up. We've got power to it, we've got ground to it, and the wipers connected to the analog 1 input. And then we have, out of pin 11, one side of a resistor goes to an LED, and that goes to ground. So what's going to happen here is, as we wind this potentiometer round, the brightness of the LED is going to change, courtesy of the pulse width modulation capabilities of the Arduino, because we've got that little squiggle there, see? So that's a PWM output there. So the Arduino is going to repeatedly read the input there, an analog input, turn it into digital, and send the PWM equivalent out here to control the brightness of the LED using PWM. And this is the code. So here we go. Setup. That's the bit you start with. You tell it which pin you want. Pin 11, where you read the capitals LED underscore pin, you substitute 11 because it's been defined as equal there. And that is the output. That's an output pin, and that's the LED pin. Here we go. It reads the analog input from the potentiometer pin, A1, into the memory, potentiometer value, and then it converts it, divides it by 4, because otherwise it gets too bright, because the input from the analog to digital converter gives you a number between 0 and 1024, whereas the PWM output requires an input from 0 to 255. So it's roughly a quarter. So, well, in fact, precisely a quarter. So we've divided it down, probably lost a bit of resolution, but that doesn't matter. And then we write it out to the pin 11, and the brightness is the number we've calculated. And it basically loops. So that is ploughing through that. Nearly 16 million, well, no, it won't, because you've got some various code in there. So probably about 1 million times a second. Boom. And you move the potentiometer and the light changes. So that's how it all works. Any questions at this point? Because that's what I'm using now to do my sound. We get the channel value, which is, you remember the 3 channels coming in, and they've all there'll be. So what I've done is I've set up the 3 channels to be connected to 3 trim switches on the radio. So 1 trim switch for the gun, 1 trim switch for switching on and off, 1 trim switch for the machine gun. And basically, for each of the 3 channels in turn, I just cycle through those, reading them, until something happens on it. I'm just waiting for the button to be switched. So the value is going to go from 1500, so that's just what's happening all the time and nothing's changing. Someone hits the button and it goes up to 2000 microseconds, the pulse width. And that will get, so basically I just test for the pulse width to be over 1750 microseconds. So there we go. Is it over 1750? Yes. Go and send the correct servo code sequence to the servo unit, sorry, the sound unit. If not, I just bypass it. and carry on. Probably go round, get the next channel, do it. And that's what it looks like. So don't, I'm doing this because I'm hoping that someone's going to be inspired to pick up an Arduino and just have a bash at it, because it's not that difficult and you can just play with it and nothing goes wrong if you get it wrong. Basically, for the channel 5, which is is the engine start-stop channel I've chosen, I read it. If the value of channel 5 value is greater than 1750, I do what's inside these curly brackets. The serial print is just to debug, so I can see it come up on a screen somewhere to tell me what I've selected. It's correctly identified what I'm trying to do. And then I select the sound I've given the name start-stop engine. Okay, and then I move on. Read that channel. If it's over 1750, see if it's not over 1750, I just skip what's in the brackets and carry on. So if nothing's changed and no one's hit any of those 3 switches, I just flow straight through here and go round again and flow straight through and round again, flow straight through. But if it does change, I then call a subroutine called select sound, which you'll see on the next page. Has the sound type changed? Yes. So basically, there's some complex stuff there. Well, it's not that complex really. But basically, I use a counter here now to do the up switches. So if it requires 3 up switches, what I do is the sound number will be 3 to start with. So it goes in, first time through, is it greater than 0? Yes, it's 3. That minus means it then auto decrements to 2. But then I go and write out 2000 to the sound controller, which is an up. Wait 100 milliseconds, and then write back to the switch position back to the middle, if you remember, was 1500. And then delay another 100 milliseconds, and then go round again. So, and then is 2 now? Is it greater than 0? Yes. It auto decrements to 1. Do another up switch and back to the middle again, go round again, and eventually sound number gets to 0. So I've done the correct numbers of ups and down to the middle. Next, what I've got to do is then do the down. So I then drop through here and do the down, and then put it back to the centre again by spitting out 1500 back to the centre. So I've mimicked the switch. What I did find was that if you're starting and stopping the engine, you trigger it with the switch position going down and the main gun. So the switch goes down, it goes bang, or engine starts. If you've got if you're using the machine gun, if you put the switch down and then bring it back to centre, it just goes, well, hardly anything really. It just makes a very short sound. So the gun sounds when the switch is down. And then when the switch is put back to middle again, the gun stops. So I've put a little test in there. If the last sound, if it's a machine gun, delay 2 seconds. So basically, a flick of the down and up gives a 2-second burst to the machine gun. So that is how it works for the sound. Okay. Are you still with me? Yeah, please.
Did you write the read channel code?
No, I did not. I used one of the libraries that are available for doing that, and it's
Because I've used hardware interrupts to do that, but there's a limit. On the Arduino that you've got, you've only got 2 hardware interrupts, and you slightly need about 6 to do what you mentioned.
well.
I use an Arduino Nano.
Okay.
Have more hardware interrupts.
All I can say is that this works. And the library might well use interrupts in its own way. I don't know, but
Yeah, but yes, you can define all the digital inputs as interrupts, but it's very complicated code to do that. You've probably hidden it from it.
yeah. I mean, the one thing I was thinking when I was writing the code was, it doesn't matter whether I use interrupts or not. I could just poll the inputs, because the computer's fast enough to do that. for my purposes. And there's nothing I need to get on with while I'm waiting for the servo signals to come from the radio. So polling would have worked. So I looked at I just decided to use the servo library, not really caring whether it was using interrupts or polling. But I'd welcome to know more about it, but I just decided to crack on past that point at this point. I had the bit between my teeth. So the motion, right? It's always difficult, isn't it, getting the motion right on a small model that's smaller than the real thing. Here's something I got off the internet which gives you an idea of what it could be like.
Hey guys, how you doing? Today we're looking at this awesome micro RC tank.
There you go, Tiger 1. There you go, Tiger 1.
Okay guys, so this is the package that the little tank comes in. Really nice.
So this will give you an idea of one of the extremes.
Quite a decent look to it.
You know, realism.
So this
and
really
motion.
struck my interest on Amazon because of a couple of things really.
It's fully functional.
It's 1 in
it says
72nd scale, so absolutely tiny. Secondly, it's a turbo tank, so I was interested
turbo
to see what
bit's
that meant.
interesting. RC
And
turbo
thirdly,
tank.
it's fully manoeuvrable with working turret, firing turret, and also onboard sound effects as well. Let's go ahead and switch this thing on. So the left-hand button fires.
See the recoil? It's good, isn't it?
Turns the turret. And when you let go, it'll go the other way. Forward is forward. Backwards is backwards. On the right-hand side here, if you want to turn left or right, you press these. So left, forwards, right, forwards.
This bit's great.
Really simple. You've got a turbo button. When you press this,
That wasn't
the tank
fast
goes
enough, was
about
it?
twice the speed.
Yeah, okay, well. I think we've seen enough of that. At the other extreme is this. Short delay while he finds first gear. Watch this bit. This bit's interesting. Tracks go loose. It almost stops. And moves off. It's going into second gear. And a little bit more tank action with a Panzer III. Altogether smaller. doesn't leak oil, it leaks smoker fluid. It's absolutely everywhere. Yeah. Okay, enough tank action. So, the point is, and I think my tank is somewhere in the middle there. Okay, but I think there are things that can be done to make it a bit more like the big fella. Right, just bear with me for a second. Yep, that's it. So, a little bit about, I'll just give a little bit on this and then we'll have a cup of tea. So give us 10 minutes and then we'll break, okay, from now. So the radio I bought was a Taranis radio from FR Sky. If I'm honest with you, it's probably a bit overkill for the job. Unless you want to, it does lots of things I don't need it to, right? And I'll give you an idea of what it how that works. But it's also got a way of mapping the physical controls to what gets sent across to the receiver, which you need to get your head round before you can actually make any use of this thing. Once you get used to it, it's okay, but it's almost like something written by an expert radio control person who's good at software and basically has architected it and presented it in such a way that, well, you would want all these features, and a lot of the features go in there in places where you think they've only done that because you can. It's so. For example, there's things called curves, which I'll come to, which you can apply a curve to one of your values, if you like, or one of your channels. But you can do that in a number of different places, and really there is no right way and wrong way, and so to a learner like me, it can get a little bit perplexing. But
what will give you a gradual acceleration?
That's what we're just about to come to, Frank. Hold on a minute, I didn't mean to do that. So what we've got, basically, you start off by having your inputs and map them to something called virtual controls. So all these controls here, the sticks, the switches, trim switches there, any sliders, you've got a knob there and a knob there and a knob at the side there and another knob there. So you've got various types of inputs, the usual suspects, plenty of them. And they're all physical. And what happens is, in the software, the setup here, you can link them all to an internal construct, which is a sort of virtual control. And then once you've done that, you can play around with them. So you can combine them if you want to. You can change them by factors. You can limit them. There's lots of things you can do. And then you've basically created a new control, which then gets mapped to an output channel. So it's really a very flexible way of taking all the inputs that you could possibly imagine, plus using possibly even some scripts and other values that you've entered and set up parameters to essentially mix it all together to get what you want. And then this comes out here where you've got those all mapped onto the actual physical channels that you've got that you're going to be able to send to the receiver. So you can write scripts in here to do calculations to influence your channels. You can write scripts to change the displays you've got available to you. You can design different telemetry screens, and it all amounts to a remarkably complex and powerful system, but actually quite daunting if A, you're new to our radio control like I was, and B, new to OpenTX. The idea is this is like the Unix of its world in a way. You can use it. Anyone can use this stuff if they want to. Not all manufacturers have adopted it, but FR Sky have been very enthusiastic adopters of it, and I think pretty much all their ARC radios have it.
Do you use it to make the tank turn by having one controls and one motor goes forward and the other one back?
That's right, that's right.
In the mixing stage?
Yes, that's right, and I'll show you how it's set up, and I'll give you a few seconds to actually work it through in your brain how it works, because I certainly had to sit and think about it before I figured out. I can't claim to have invented the way that the channels are mixed to make that work, but I do understand it just about.
Basically, you're the tank commander, and the Arduino is the tank driver who takes your instructions.
That's a great way of putting it, Frank. Yeah, and I don't have to say please and thank you, and he never gets it wrong.
You never want a tea break.
Never wants a tea break, no. So what you can set, you've got this little LCD screen on the radio, but you've got about 1 billion settings that you can go through and 1 billion screens. So the last thing you really want to be doing, it's like doing sort of keyhole surgery when you're setting up your radio. If you try and do it just by using the screen on the radio and all the buttons, it's sort of really old-fashioned stuff, you know, up buttons, down buttons, double clicks, long clicks. I mean, sorry, that's just not acceptable to me. So what I use is the software that you can get for your PC for OpenTX, called OpenTX Companion. And basically, it allows you to tinker with all your settings on the screen. Much more real estate, got a mouse, much better. So there's your file, open a folder to get a file called telemetry.otx, opens it up, and in that file, magically, I've actually got 4 profiles for my Tiger. So I can have as many profiles as I like, pretty much. And the profiles essentially are different combinations of the settings and scripts and whatever have you.
Configurations.
Configurations, yes. So here I've got one that goes slow. That's what it's currently set up as. The Tiger's tame but fast here, so that gives me a fast option. And that's the original setup. If I tried to use that original setup now, that profile, it wouldn't work very well, because in the process of setting up my new way of controlling the tank and the sound, the old way is now rendered obsolete. So some of the things wouldn't actually work anymore. But hey ho. That's there for history, really. But this is great because you can keep things saved, you can back them up, and then what you do is using a USB cable, you connect it to your radio and squirt the config down to the radio. And you get you don't just get one of these sent down to the radio, you get the whole lot. So basically you get this whole config file is sent down to the radio, and before you know it's all there for you. So if you're getting into OpenTX, you've got to do it this way, really, in my opinion. We'll stop in a minute when I say the tea's ready, okay? But here's where the rubber hits the road. So here we got the physical input names. So I can't remember what SD stands for, but we've got elevator, ailerons, rudder. What's the fourth one? SD on the joysticks. Anyone? Throttle, is it? Yeah, okay. Could be, couldn't it? This percentage. So these are essentially the 4 that arise from the joysticks, the 2 joysticks. Each joystick has got 2 dimensions, and so you've got 4 there. And I've mapped them onto these. Elevate, this is the virtual name, I1, elevate, and that makes the gun go up and down. I4 is traverse, so that makes the turret go round. And these 2 are concerned with the tracks. So elevate and aileron are both on the same joystick, the right-hand joystick in this case. You may be asking why I've sequenced them in the way they have. I haven't actually tidied up some of the things I did, in order for your consumption. I've left it as it is, as it evolved, as I built it and configured it. So if I was start again, I might have actually grouped these slightly differently. I might have actually given them slightly different names as well, because what you'll find, to make me confused and you probably more so, is I've actually got some of the names a bit weird. And so if you look at the name and think you know what it does, you're probably wrong. So, because for a start, elevate, which would be moving the stick backwards and forwards, is not. It would be unfair to call it internally in the radio the left motor. It's not. Because moving the stick backwards and forwards actually ends up controlling both motors. So that's misleading. And so that's not right motor, because the aileron is the left to right on that joystick, which doesn't map to the right motor at all, on the right track. So there we go, layers of confusion. The 100% simply means that whatever goes in here goes out to the virtual thing. So for example, if I push the joystick to maximum forwards, that would be this one, elevator, and that would be equivalent of 100 in OpenTX speak. If it's in the middle position, it's 0. If it's fully back, it's minus 100 in OpenTX speak. I don't know whether that's the same in other radio controls, but so that means that if this is indicating 100 from its stick position, this is will also indicate 100 there. So they're one-to-one mapping. If I change that to plus 50%, then half of this value would be reflected here. If I put minus 100 there, it would flip the polarity, as it were, of this number. So if that was indicated, if the elevate was fully forward and indicating 100, then this would be indicating minus 100. So essentially it's given it the complete opposite. But the default is just 100, and unless you've got a very good reason to change it from 100, don't, would be my advice. And pretty much everything here in OpenTX has this sort of thing called trim. Those of you who fly aeroplanes will know what trim's all about. It's just about tweaking the inputs to compensate for certain factors, probably part of the aerodynamic factors of your aeroplane or whatever. And so for example, to go in a straight line on your aeroplane, actually you might need the aileron at 2 instead of 0. So you can put a trim value in here to make it to just make that zeroed on 2 rather than 1, if you see what I mean. So rather than trying to tinker with this number here, which wouldn't work very well. So it's an adjustment factor. So, and then finally this one here, I6, is where I've done the volume. I'm not really talking about this today, it's something I've talked about before. It's where I've taken this channel and simply assigned it to one of the rotary knobs on the controller, on the radio, and in the tank I've taken, from the receiver, I've taken a lead to a bog standard servo which is connected to the volume control of the sound device, so I can remotely control the sound volume. So that's it's about as straightforward as it gets, that one. What I'm going to do now is I'll probably stop, because the tea's probably imminent now, and I'll take the lid off the tank so you can have a poke inside, and then we'll carry on with we'll go straight to the how you go left and right and backwards and forwards when we get back after our tea break. You've got a motor controller there which controls both the big motors, and then another motor controller for the turret, the motor controller B. And here's the main power distribution. And that's the remote control thing for that. And that's the 5 volt converter that powers the Arduino. So the volume control is jolly handy, I must say. And which is quite something when it hasn't got a gun fitted, isn't it? But there we go. So, and when I start it, moving it towards you, Ian, you can do it quite safely. I wouldn't have stood there initially when I've... And also, something I'll come on to after the tea break, but if you watch, I'll just put this into max, and it doesn't actually go leap straight forward to maximum speed. Right, to the question of how to steer the tank using the throttle. So if this just work through it, I think it's okay. So this is a representation of the stick. That's actually one stick, okay, but to show how it works, this is the right hand stick. Move it forwards, you get plus 100 on the I2 virtual input. And then if you move it sideways, you get minus 100 through to plus 100 on the I3. Ignore the fact that that's implying left motor and right motor, just ignore that. So channel 2 is fed out to the left-hand track, and channel 3 is fed out to the right-hand track. So here we've got the two ignore turn and drive. The two tracks are there, and the inputs, both of which come from that one single joystick, are there and there. So the left track, so imagine this, right? So if you push the stick right forwards, but not sideways in any way, so all it's doing is giving I2 100, so I2 value of 100, okay, and that gets input into both tracks. Right, and then if you have it down to minus 100, so what's happening there is, because that's at a value of 100, that says 100, and the L2, I2 again 100. So that means that both tracks are receiving a positive 100. So basically both tracks will be moving forwards together at the same speed. Similarly, not similarly in fact, it's slightly differently. Let's just imagine that we don't move the stick forwards or backwards, but actually what we do is we waggle it from side to side. So if we move the stick to the right fully, what do we expect the tank to do? If I don't move the stick backwards or forwards, it's just sitting at 0.
Turn on a sixpence.
Turn on a sixpence, Frank, exactly. So the turn on the sixpence scenario, let's see how that works. For a turn on the sixpence, we need both tracks to be going in the opposite direction to each other, don't we? So let's see how that works. So if that's plus 100, so we whack the stick right over to the right, but not up and down at all. So that means I3 is 100, and that is 0. I2 is 0, because 0 is the central position in OpenTX. So we've got I3 at plus 100. So I2 is 0, I3 is plus 100, so the weighting on that is plus 100. So simply the left track goes forward at 100, in other words, flat out. However, this is the right track. Again, I2 is 0, but I3 is 100. But here we've got a minus sign. That effectively means that now the right track has got a minus 100 going out to it now. And that means the track is going in the opposite direction. If you were to switch the stick right over to the left, then you've got I3 at minus 100. So I3 at minus 100 would mean, because that just gets passed straight through there, it means that the left track is going backwards now. And because it's at minus 100, I3 gets flipped. Minus times a minus is a plus. So now the right track is going forwards. Now I won't necessarily go through this as a mind game if you were actually moving the stick forwards and to the right. But to suffice to say that if you've got your stick pretty much at maximum, and then you just move it slightly, so it's maximum forward, so you're careering ahead at flat out, and then you move the stick just slightly to the right, because it's not maximum to the right, and the tracks are going in different directions, and you've got a plus value here, what you find is that you get a nice graduated turn. So I can just move it along, and then just nudge the stick to the right, and it'll slow down one of the tracks so that it's going slower than the other. To fully sort of get your head round it, I found it was necessary to sort of pick some values for both the channels and just do the computation through this rather straightforward but powerful piece of mixing in the radio control machine. Everyone happy with that? I think it's quite clever, actually. Very, very ingenious. Because I did think about how to do it, and then I realised. Then I thought, oh no, I just can't figure this out. I'm going to use the internet. Right. So that's that. So that's using the radio. Nothing there that's going to hit any of my issues that I've got with the tank. Just to sort of wind back a bit. That's just interesting. And here the final step is where we map those values that we saw on the previous screen to the actual channels that are going to get transmitted to the tank itself. So, in fact, I don't have any spare channels, do I? I've got the 8 for the volume machine gun, 88mm and volume. No, I don't have any spare channels. They're all used. Now, obviously you can put another bit of trim on here. I don't know why I've put -3. I think I was just playing about or found that one track started before the other. Because, I mean, the motors aren't necessarily identical. Jim?
How much is the cost of the control unit then?
The radio?
Yeah, the radio.
I think that was about 100 quid, something like that, 120. That sort of ballpark, I think.
The transmitter?
The transmitter, yeah. And I think the receiver was 20 odd, 27 or something like that. And I think the telemetry was about the same, about 20, 25, 30 quid, something like that. These are limits that you can provide to the output. So, for example, if you've got servo controlling the ailerons on your plane, and because of the compactness of the space and the ratios of your levers and things like that, you might want to actually put a limit on there to stop the servo going too far, for example, and tearing your plane apart. But of course that doesn't really have much use in what I'm doing at the moment. The thing you might notice here is CV3. So this is where I've applied a curve to the left and right tracks, to the signal going out to the left and right tracks. So I've used a curve, and I've used a curve to try and make it easier to use. Here's how I've done it. Oh, not yet. This is some telemetry stuff. I have to override the trim switches in order to do that. This is something that's quite easy. It's well documented, but I'm not totally sure why I need to do it. Okay, so curves. This is about the relationship between what the stick position and your mixers are saying and what's actually getting sent out to the receiver. In actual fact, you can apply a curve at the mixing stage if you want to. And there doesn't seem to be anything other than a general, actually probably better apply it at the final stage if you don't have, if you've got a choice, right? Just a bit of a convention perhaps emerging there. I mean, this speaks for itself really. So this is the input. So that'd be like 1,000 microseconds to 2,000 microseconds or something like that, plus 100 on the radio, 0, minus 100. But either way, you're moving the stick forwards or a dial round or something like that, and the output has a curve applied to it. That would be typically a linear, and that's just the default situation. But you can do something like this. Well, not quite like that actually, because although it calls it a curve, it's generally a polyline or multi-point line is what you really get. So here's the curve. Here's curve number 3. Why is it curve number 3? It's because the third curve that I settled on. And curves 1 and 2 aren't worth bothering with. So how does this work? So that's got the input across here. So that's 0, or the joystick in the centre, for example. That's the joystick in the centre. And across here, as I move the joystick across here, the output signal ramps up fast, and at this point, and then it goes off slowly. So here's the numbers for it. So that maximum there is 35%, or 35 instead of 100. The default out of the box is a straight line going up to maximum there. But applying this curve means that as I move the stick to the right, the signal ramps up very quickly. And then all of a sudden, the signal ramps up slowly as I go up here. And it's at the point where the stick's sending out 5 and the radio's sending out 15. Okay? Here. Why is that happening? Well, basically what's happening is you can move the stick forward and nothing happens. And then all of a sudden the motors start. And it's just a characteristic of the motor and the way pulse width modulation gets applied to the motors. It just means they just don't start unless they get enough juice through the pulse width modulation. And it tends to happen around about there. So when it gets to about, hold on, where are we? It's this one, isn't it? So when it's getting 15 there out of 100, which would be, I don't know, 1,650 in terms of microseconds in pulse width modulation terms. And so I want to go to that point quickly, and then, in fact, the motors literally start just after that, because I wanted to get up there quickly. It'll probably start just a little bit higher than 15, about 16 or 17. So as I now go up this very gentle curve, I don't lurch forward quickly. It makes it much easier to start and get that biting point just right. In reverse, it's pretty much the same, although I've just decided to arbitrarily make the tank even slower in reverse, maximum speed. I chose a 5-point curve. You can choose curves with generally any odd number, up to about 13 or something like that. It could go higher, but I didn't bother exploring higher because basically I figured that 5 was actually good enough for me. Well, this might be where I'm heading. This is what I call Tiger fast. So if I just switch the Tiger to a different profile, and I want to drive it from the display ground over to the car park for my car, it'll take ages if I was in the slow one. So I can just go in the fast one and go flat out, assuming I've got any battery left, which I didn't actually.
Can you change this on the fly?
Now you have to stop the tank, and well, it's basically you have to reselect it on the radio. I haven't tried doing it on the fly, actually, Frank. I've got a feeling it'd probably work. Would it?
Yes, because you can have more than one curve, which can be activated by another switch with a logical switch.
Oh, okay. Well, that's probably what I should do. Yeah, that would be the easier way to do it, rather than changing profile, wouldn't it? Well, that's a thought, isn't it? There's so many switches that the chance of them getting the right switch is fairly slim. But yeah. Okay. Fair point.
You can also get the radio to tell you what mode you're in, so as soon as they switch it, it'll start telling you you're in fast mode.
Okay, yeah. Get it to make a sound. Stop that boy. Right. Okay, so a lot's been achieved just by using curves. We've compensated for the motor start, slowed down the stick response, limited the maximum speed, but it's still difficult to control smoothly at low speed. Why is that? Realistic driving, yeah, there's going to be some practice involved here, clearly. And even with with my dexterity in the stick, I'm going to have trouble imitating gear changes consistently. So I can't do, you're about to tell me I can, but I don't think I can do those however things in the radio very easily. I looked very hard, so I really needed some kind of conditional program loop in the radio, and it didn't have it. It could even execute some code, but it's really all about configuration rather than processing.
Could you not go back to the curve and put a kink in? Just a little dot fast and then slow again, so you bring it back to where you were. But that little kink gives it a jerk, but it looks like it's changed gear.
Potentially. It's worth trying. It's worth, yeah. It's with whether it would operate realistically both ways through it, but it's worth experimenting with, and I haven't got that far yet. So this is what happened here. So that's really what I want to achieve. As I move the stick up, don't note this is time along the bottom now. I'm just accelerating. This is a time profile of the speed now. Tank's stationary. I'm moving the stick up, and it gets to a point where the motors start. And I speed up a little bit and then go along slowly. And that would be nice and smooth, wouldn't it? But it doesn't work like that. What I found was that the signal to the receiver that went across to the signal that the Arduino was receiving along the motor channels was actually fluctuating. Now it could be because, you see this? That's me being steady, right? I haven't had a drink tonight yet. But that could be my finger on the throttle, just quivering, yeah? Tony will tell me that's why I'm not hitting the targets when I go shooting as well, because I can't hold it still. But either way, that was happening. Doesn't matter why, in that sense. And what you can see here is that it kind of causes it to judder a bit, because when you're on this threshold area, sometimes it's ready to move and other times it's not, and so it literally does quiver and look a bit jerky. So I dumped the signal I was receiving out onto the debug screen with the Arduino, and here's what I found. I was measuring these numbers here. So these are in milliseconds, 1.664 milliseconds. And these were the deviations from the average. Okay, now I felt that was quite a high deviation, really. It was non-trivial. So I thought, well, again, is this a problem here, or is it me and the stick, or is it the Arduino and the routine it's using to read the signal making the errors?
Is your joystick spring loaded?
Yes.
Is it easy just to have them?
I'd have to switch to the other one. The other joystick's not spring loaded, or I could actually buy a new joystick and replace the joystick in the controller, I suppose. Yeah, good point, Frank. So I thought I wanted to find another way of checking this, so I checked it, and what I did was I connected a logic analyzer there. Anyone know what a logic analyzer is? You all know that, yeah? Basically, it's an oscilloscope for looking at digital signals. And if I could see the same thing in the logic analyzer, then it's probably not the Arduino that's at fault. I'm just dealing with a fluctuating signal for one reason or another. So there's the logic analyzer for the grand sum of £11.95. You get and you get a nice little ribbon cable where you can connect these 8 channels. It's got 8 channels, and you connect them in. There it is. That's the logic analyzer up the other way, and there's its ribbon cable. And I only bothered to read one of the channels, the channels, so I only needed one of these ribbons to go down there. And connected the other bit to my laptop, downloaded some freeware, and off I went. And here's the screen I got. Actually, this isn't the screen I got. This is an example screen, but it isn't what I actually got in the experiment I was doing. But basically, down that one channel, there's the PWM signal, and roughly every 20 milliseconds, well, okay, 18.1 will do for me. And this is just, I don't think I was touching any of the controls. This is just something happening. And so here's the time base along the top there. And interestingly, there's the sample rate, and that's the maximum number of samples. This all gets dumped to a file. So I'm taking 1 million samples a second, so it only takes a 10-second clip, and it all gets dumped straight into a text file. And it's the quickest way to create a massive file. Honestly, it really is, because I can ramp that up, I think, to 10 megahertz. And it's fascinating. Of course, I did a schoolboy error at the beginning. Choose a suitable sampling rate. I just didn't think about it. I thought, a kilohertz is quite a lot, isn't it? It's not, is it? It's not, because it's about the same. So a kilohertz is once every thousandth of a second. Well, I'm actually measuring things that are down to a millionth, because I'm measuring microseconds. I'm not measuring milliseconds. So if I only sample every thousandth of a second, I'm just going to get the same number coming up every time. It's not going to reveal any fluctuation of 4% or something like that at all. So I had to up it to a megahertz, which is microseconds, which is so I can see a 1.683 milliseconds, or 1,683 microseconds. And then I noticed that it read exactly the same, not the precise numbers, but it was showing exactly the same fluctuation that the Arduino was measuring. So what I really needed to do, if I couldn't get the brown line, I needed something like the green line. So what I did was I took the average. I simply took I took a running average. So don't get too bamboozled by this. Imagine if you have a pen and paper and it's all going very slow, and you have a table here called buffer, and it's got 5 entries. And every time there's an entry, and every time you measure the signal, every 18 milliseconds or whatever it is, you write down the new number that you've got. And then another 18 milliseconds go by, you write down the next number, and the next, and the next, and the next. When you get to here, you get a rubber, and you rub that out, and you write the new number again. And then you get to here, and you rub that out, and put a new number in, and so on. So you're looping round. So this buffer effectively always contains the last 5 signal recordings. So what I do in the software is I set n to 0, because n is going to be an index into this buffer in the software. I read the channel for track 1, I store it in buffer brackets n, and what that means is if n is 0, it goes into that one, that slot. If n is 1, it goes into that slot, and so on. So then this one sets smooth track 1 signal to the average of buffer 0 to 4. So that means just calculate the average. And then I increment n. Is n 5? Because if n was 5, I'd have gone off the end of the buffer. So I don't want n. So if it's 5, I just flip it back to 0 and go round and start again, go collecting signals in, overwriting what I'd already got. So I've always got the last 5, and I take an average of them. And hey presto, it works. It just transformed that from a quivering sort of jerkiness at that transition into motion into something that is much easier and smoother to implement.
In analog terms, that's like eliminating spikes with a capacitor.
It's a low-pass filter. Yes. And just to show you, the code's pretty much identical to that. So there we go. Set the track pointer, which is the index, to 0. I read the channel 2, into that variable. And then I store it in the array or the table called track ac, indexed by that number. And then I calculate the value, the average. 1, 2, 3, 4, 5 elements in the table divided by 5 goes into that value. And then I increment the index into the table. And then if it's 5, if the index is 5, I just set it to 0. It's just as the flowchart, and that's in C. So it worked very well. I'm very pleased at that. And it does help me when I try and make it look realistic, so that's good. A little bit, just quickly touch on this because we're getting on for time. Motion, inertia. So it's a big old tank. I'm trying to emulate something that's 55 tons in something that's 80 kilos. So I need to make it look as if it's lumbering a bit, for want of a better word. So I got myself, this really challenged me to think, right? How do I do that? You know, what is inertia like? There it is, inertia. Basically things are at rest, staying at rest, or keep going at a straight line unless they're acted on by some other force. Don't know if that's helpful at all really, but anyway. So I thought what I needed was maybe just play around with addressing the acceleration. So if I whack the stick right up to the top, maybe I don't want the tank to go accelerate at that rate. Maybe I want to just cut the acceleration back, limit its acceleration. Would that help? It's only partially helped actually, because that was back to that bit I was talking about booking an appointment with first gear and it lurching forwards after a while. Because what tended to happen was I'd move the stick forwards and nothing much had happened because I'd got that delay in the system for it to catch up slowly, and then so I'd push the stick forward a bit more, and then before I know it, it's racing along. Maybe it was practice, maybe I should have tweaked the numbers a bit more. But anyway, also the problem was here. I didn't want that delayed effect to cause me trouble when I was loading the tank into the car or not. Because last thing I wanted was to move the stick and then find the tanks speeding up without me doing anything more. And if I wanted it to stop, I wanted it to stop straight away. I didn't want a deceleration algorithm to slow down the rate at which it stopped. If it was about to fall off and I wanted to stop it, I wanted to stop it. So that was no good. So what I did was I basically put a system in place which basically said the output isn't going to go up as quickly as the input. So if the output's bigger than the current, what it was before in the previous time interval, then I'll only allow it to go up by a certain amount. And then the next time interval, is the stick still telling me to go faster? Yes, okay, well I'll go up a little bit faster by that same increment again. Am I there yet? No. And so basically you limit the acceleration like that. And eventually you get to the point where it'll merge with the stick position. Partially successful. I think it might have a place in the overall model, but it's not the whole answer. What I did was, and I won't go through this code because we're running out of time, but that I had a cut-off, so I didn't apply that inertia or that acceleration limiter in this area, in between an arbitrary high and low cut-off speed, so that it was just simply reflecting what the throttle was saying. So I haven't got time to go through this now, but you'll see the slides published, I guess, in the video. Can it be improved? I thought about perhaps making the acceleration a function of the speed as well. So if the speed's really high, the acceleration is probably not going to be very aggressive, whereas if it's low down, it might be, I don't know. I might have even thought about looking up at the engine power and torque curves and seeing if they told me anything about how I could actually emulate those. And I thought perhaps it would be useful to have some feedback from the motor speed sensors rather than just using my eyeball to estimate and judge that way. But I haven't got that far yet. And then finally, the final thing I'm going to do next is gear changes. This is work in progress. You saw what a tank did initially, didn't you? You know, it's not quite the same as a car. It definitely lurches. It's not very slick. It's a wonderfully complex and an incredibly advanced system, but it's still pretty clunky in that big old tank, which is ultimately a bit underpowered. So I will keep at it with gear changes, and I thought, you know, I need something like this going on, where basically as I move the stick along, the engine note changes like this. So I need independent control of the engine note now. So the engine note doesn't match the track speed. So at the moment the two are wired together, but I need to separate those out. And as I move the stick this way, you get the change in tone of the engine. I do need to implement something for the actual tracks as well to synchronise with this, to show the sort of behaviour that the tank makes when it does change gear. It's more like the motion of the tank's a bit more like that. The speed's a bit more like that, rather than quite so sort of like that. So these jagged teeth might need to be curved off a bit. But basically, this was the tally after I did all these things. So I was quite happy that I've made some progress, but there's a lot more scope for getting this better. And when I can take some time off the Sterling single, I'll get cracking on this. So that's the end for now, but I fully anticipate the opportunity of boring you with talk number 4 in about 3 years' time. Thank you very much.